It is a great pleasure and an honor to have with us Dr. Charles TAHAM at the US White House Initiative for Quantum Computing. He got his PhD at the University of Wisconsin-Madison, working on different aspects of quantum information, semiconductors, and related topics. Then became a postdoc, spending time at Cambridge University in the UK, also at Tokyo University and other places. And then eventually joined the Laboratory for Physical Sciences at the University of Maryland. And then joining the White House. He has done pioneering work of importance in different areas of quantum information, quantum computing, and related topics. And he has been influential in the field at different levels, scientifically and policy-wise. And he's going to talk about the USA National Quantum Initiative. Welcome, Charles.
Hey, good morning, and thanks, Franco. Good morning from America. I am at my daughter's bus stop this morning, so I apologize for using my mobile phone in the background, and appreciate my hosts, driving the slides for me. But it's a real pleasure to be here. I'm going to spend 30 minutes just telling you about the National Quantum Initiative here in the White House. So let me just start by motivating quantum information science. I'm going to turn off my video just so it's not bouncing around too much.
Yeah, okay.
What I like to say, next slide. What I like to say is there's a very good case to be made that information technology is a result of our understanding of quantum mechanics. And IT is a large reason for our prosperity. So transistor, the laser, magnetic storage, magnetic resonance imaging. These are, kind of vital technologies in our life nowadays. And these came about in no small part due to our understanding of quantum mechanics, like the most basic parts of quantum mechanics, that particles are quantized, they're electrons, they're photons, and that there are energy levels. So with that kind of basic understanding, Quantum 1.0, we were able to create these amazing things. Next slide. And for computing, over the last 60, 70 years, we've built up this abstraction, what should we call computer science or information theory, the zeros and ones that make up information, having that as a base, we can then build programming languages, you can build assembly languages, you can build compilers and operating systems. And that has served us quite well. But it just turned out to not be completely true. And starting 40 years ago in the 80s, people, a few physicists here and there started thinking, well, if we really started to think about information science based on the laws, not of these zeros and ones that we humans came up with, but the actual laws the universe uses to run computations, namely quantum mechanics, well, what would be different? And that's quantum information science to me at the heart of it. Next slide. Feynman usually gets credit for a lot of things, but one of the talks he gave, posed this from a physics point of view, that we know that it's hard to calculate properties of quantum systems on a classical normal computer. Namely, if you add a degree of freedom and you take that naive approach of just writing down a matrix, the matrix scales exponentially as the size of the system grows. So it gets harder and harder. And intuitively, you'd say, well, nature doesn't have that problem. It solves for the ground state pretty fast. And why is that? Well, maybe it's because it's just operating by the rules of quantum mechanics. And if we could build a computer that operated by those rules, maybe it could be much more efficient than the classical computer. So that's kind of the physicist's point of view. And indeed, go to the next slide. For certain problems, we've discovered that quantum computers and quantum systems can be more efficient. And in terms of a definition, and this is going to get important when we talk about the policy, because many different countries define quantum information or quantum technology differently in their national programs. We define it this way, that it really, quantum information science and technology has to take advantage of these newer properties or more exotic properties of quantum mechanics, like superposition and entanglement, quantum measurements, and so on. And those enable new types, fundamentally new types of sensors, networks, and computers. So that's quantum 2.0, or quantum information science as we define it. And so when we talk about the National Quantum Initiative, it's broad in the sense that it goes beyond computing. It includes sensing and networks and enabling technologies, but it really tries to focuses on this new field of quantum information science, not all quantum things. Next slide. And at the end of the day, why this is important is that we strongly believe that quantum information science is a foundational shift in information technology. And that doesn't happen very often. And a great example of that are large-scale quantum computers, where we've done quite a bit of work and shown that, at least for a few problems, a quantum computer that's big enough and good enough will dramatically outperform any classical computer you could build. The most famous example is the Shor's quantum algorithm for factoring a prime number. And that problem, that classical problem of factoring a number, is the hard thing that public key cryptography, or the cryptography we use to do transactions on the internet or with our bank or national security communications, that's the hard problem which all those systems are based on. So it puts immediately at risk the encryption standard we've used for communicating with each other. And after quite a lot of work, I think it's still believed that a quantum computer will exponentially outperform a classical computer for that problem. And then there's the science. This is still a very active area of research. What will a quantum computer be useful for, and when will it be better than a classical computer? But there's a lot of evidence that you're going to be able to do really cool science with it that you couldn't do otherwise at some point, at some size of quantum computers. And then at some level, they'll actually be economically useful, meaning if I give you a quantum computer that's big enough, you can do something that's valuable to somebody. You can calculate the properties of material or design a new chemical. You can do that better than anybody else could with their normal high performance computers, and then make money, right? So that's sort of the utility aspect. That's out in the future, and we're trying to understand when that will happen. Next slide. So with that context, I'm going to talk to you about how the United States has approached this field of quantum information science, which is now, you can argue 30, 40 years old, but it's still it's still quite emerging, in the sense that we don't have all the answers. There's still a lot of science to do, and we don't know what the technical impact will be. Next slide. Let me begin by just telling you about how the United States system works, because it's, each country does science funding in a different way. Our approach is very federal, meaning the power is quite spread out. So we have in the US, the President's Office, where I work, the Office of Science and Technology Policy is one part of that. They make recommendations and recommend to Congress what funding should be in R&D, as one example. But Congress ultimately appropriates or gives the money to the agencies to implement it. And the agencies also play a role. So we have many different funding agencies to fund science: the National Science Foundation, the Department of Energy, the Department of Defense's DARPA, as an example, although there are many different funding sources within the DoD, NIST. So there's many different agencies that all have their own missions, but to fulfill those missions, they fund science. So NSF's mission is to promote the advancement of science. It's quite broad. Whereas NIST, the National Institute of Standards and Technology, at the end of the day, they're tasked with making new standards. And so they tend to fund research that advances that goal. So within all those missions, the agencies propose their own budgets, which go to Congress. And then Congress, and there's this loop where everybody tries to work out how much funding should be spent each year. And coordination happens in places like my office or in subcommittees in the White House. And in for quantum, we actually have two, and I'm going to get to that next. So next one. So I mentioned that quantum has been around for a while, and agencies have indeed been funding programs in quantum information science for decades now. But it really came to a head a few years ago as the field emerged and started getting a lot of interest from industry. The industry starting to put big investments in, and there was a growing recognition that we needed to kind of rebrand the national effort and double down on investments. And that became the National Quantum Initiative Act, which is a law passed by Congress in 2018 and signed by the president at the end of in December 2018. That legislated a few things. It called for Department of Energy, the National Science Foundation, to create new national quantum information centers across the country. It called for NIST to launch a industry consortium. It created the National Quantum Coordination Office, which I lead here in the White House, and we have 5 people at the moment from different agencies who are loaned to the White House to help coordinate across all the agencies. And it created eventually 2 subcommittees in quantum in the White House to help coordinate this activity. Next slide. Yeah, I want to stress that it's not just those 4 or 5 funding agencies. There are many agencies, 14, 15 and growing, who care about quantum. You know, either their mission is to fund R&D, research and development funding, or they want to eventually take advantage of quantum technology that comes out. So NIH might be considered an end user where they want to use quantum sensors to advance their mission to health research by imaging the brain or whatever. The U.S. Patent and Trademark Office, you know, their mission is to do patents and trademarks. So this new field, they really need to understand how it might change their job. So all these agencies come together in the White House to develop a national strategy for how we're going to tackle quantum. And in addition, there are 2 outside groups: the advisory committee, which advises the president, external experts in the U.S. will advise the president, and then the Economic Development Consortium, which represents industry. Next slide. So around the same time, 4 years ago, we wrote together, across these 13 agencies, a national strategy. And it has 6 main policy drivers. The science is number 1. Invest in the right infrastructure to enable that science and technology development. Build a workforce for this new area. Nurture this new industry. Balance the economic and national security implications of quantum. And right from the beginning, quantum has always had this cryptographic application. So we really need to consider that right from the start. And then to continue and expand international cooperation, because we all realize that quantum has always been a global endeavor, and it's such a broad field that we really need to continue to work together to explore it. And with that strategy, we didn't set about, trying to increase the funding. And over the last few years, the funding for quantum in the US has doubled, as you can see in the bottom right. And then we've augmented that strategy with new policy recommendations. So at the end of the day, what my office does is try to get the agencies to talk together and work together, but also develop policy recommendations for Congress and leaders in the agencies and the White House so that they can decide where the funding should go, what we should put our focus. Next slide. So in terms of results, now 3 or so years later, there are 13 new National Quantum Information Science Centers, 5 from DOE, 5 from NSF, 3 from the DoD and IC. LPS, where I came from, is now has a center. These are spread out mostly across the country. And again, if I had to summarize, those 6 policy drivers, they come to 3 things. First, get the science right. Focus on the science problems that matter to push the field forward. 2, enhance our competitiveness by understanding the implications of quantum and driving the technology for useful impact for the country. And three, enabling our people. So trying to create new jobs, understanding how to get more people involved in the field, workforce development, and so on. And the three things on the side there are strategies that are a bit more specific that add to our overall national strategy. So the first Quantum Frontiers report outlines our input that we've gotten from the quantum community, mostly in the US. It tries to collate the big grand challenge problems in the field that still need to be solved. For example, what is the correlated error in qubit systems? How good could quantum sensors be? And so on. The next two reports dive into technology specifically. So what should the US be prioritizing in quantum networking? What should the US be prioritizing in quantum sensing? And the results are different because they're at different stages of maturity. Our most recent report, the quantum sensing, bringing quantum sensors to fruition, is more about how do we bring these amazing sensors that have been developed in the lab to market or to actual useful application. So what would it take to do that? Which agencies should try to carry that ball forward, and how much more money do we need to do it? Whereas quantum networking is more about, well, we don't know the ultimate applications for quantum networking yet. We have an inkling of what they could be used for, but there still needs to be work done on application discovery. And at the same time, we should continue to defend core components like qubit transduction between qubit types or quantum repeaters, which we know will be valuable no matter what, for many different topics. Next slide. Secondly, just this concept of enhancing competitiveness. How do we keep the U.S. moving forward? Is the end goal. So part of that is helping this new industry grow and survive. Where they're still trying to find the applications. And we're in this nascent stage where we have technology, it's moving forward, but we're still trying to understand what is it good for? How far is it going to take us? How long is it going to take us to get there? And at the same time, we recognize that we have to take these investments, seriously in terms of protecting them. There are entities who want to steal the investments being made by companies and by the U.S. and our partners. How do we sanely create a secure research environment so that we can keep doing the open science that I think the whole world has benefited from, but at the same time recognize that we may have to be a little more cautious than we have in the past. And the core part of that is working with international partners, other countries who have their own quantum initiatives, and trying to work together to develop export control regimes that make sense for this new type of field, and research security protocols that are fair and open and create healthy research environments. Next slide. And then finally, maybe most importantly, is how do we create new people in the field? Because we have in the U.S. we have a big shortage of talent. We have a hard time hiring into the government these days. The companies are have more positions than they can fill in quantum. Overall, in STEM, science, technology, we have greater demand than we have supply of people. So how do we, again, educate more people really around the world who want to go into hard science fields? So we spent a year or so working across the agencies to develop a workforce strategy. And parts of that you can see in the middle here. We've launched a Q12 education partnership. K-12 in the US is kindergarten through high school through 12th grade. The goal here is to have companies and professional societies and educators like high school teachers come together to develop curricula for all age groups, to introduce them to quantum as an example of the emerging industry of the future, and get them on track. And to me, it starts with having good careers in this field, and I think there are a lot of great careers in quantum and adjacent fields like autonomy and AI and so on. But then giving people the experiences and the education to actually be successful. Another part of this is World Quantum Day. So U.S. really took a big step forward this past April by participating in the first World Quantum Day. We hope that grows every year. And you can go to our website, quantum.gov, and see some of the things we put out. And for example, we created, working with partners across the U.S. who have created modules like 1 or 2 hour long classes that can go into high schools across the country. And I think 300 or so were deployed on World Quantum Day, as a test, and those are going to grow every year. Next slide. And this concept of talent is really important to us, and it's not just about moving the science faster. It's about, at the end of the day, our overall security, because we want more people who believe in democratic values, who believe in an open and fair competition in science and technology. So one of the first products that the second subcommittee is actually 2 subcommittees in quantum in the White House. One of them focused on the civilian agencies' national quantum initiative programs. The other focused on the economic and security implications of quantum. And this subcommittee, second subcommittee's first report was really about this question of talent, because at the time, 2 years ago, there were different forces within the country, restricting immigration from certain countries, especially ones who are focusing on military, fusion fields, and frankly, trying to take advantage of our open system. And the concern was that restriction would expand, and we would start to limit the amount of talent coming in from the rest of the world. And what this report really says is, well, first of all, the U.S. is completely dependent on talent from all over. I'm the son of an immigrant. A lot of our greatest scientists have immigrated. We need to keep encouraging that. It makes no sense to try to stop that. It's a net positive. And we have to work with countries around the world to lift all of us up, right? So that's really the recommendation here. But at the same time, just be cognizant that universities have kind of had it easy the last 50 years. They didn't have to worry about these types of research security questions, and that has to change a little bit. We need to be a little bit more cognizant of risks of cybersecurity and so on. Next slide. Another role that we have as a coordination office in the White House is to talk to the community, talk to universities, talk to industry, and so on. So we had a big event about a year ago where we brought in a lot of the U.S. companies working in quantum as many as we could fit in the room at a time, and just talked about some of these issues, like their workforce needs, how they are, what are the technology pitfalls, and where the government help, how are they protecting their investments, and so on. Next slide. And at the end of the day, again, representing the policy office, the number one question we get is, well, what's a quantum computer good for? What's a quantum sensor good for? How is it going to matter to my constituents, the congressmen and senators who represent people across the country? How is this technology going to matter to their lives? As, for example, the Global Positioning System did, which is built on quantum clocks. So what's the next quantum clock, for quantum information science? So this is sort of how we think about impact. And, in an ideal world, we could fully understand that this technology that's being developed in the lab will eventually have this much impact on society. We don't know that now, but we want to keep refining our understanding of how different technologies will matter. So, probably the most famous one, as I mentioned before, if you had a large fault-tolerant quantum computer, it could break encryption that we use today, in all aspects of our lives. So that's a existential technology. We have to update our cryptography to protect ourselves from that whenever it happens, 10, 20, whenever it happens down the road next year. Next slide. And then, as taking quantum computing again as an example, where will this investment pay off? It's still quite an open question. That we have a whole slew of algorithms now beyond cryptanalysis, including chemistry, material science, optimization. But I would say the field is still pretty nascent in knowing when and how much they will actually matter, compared to the really great codes we've developed over the years for classical computing. And part of this is because we don't have quantum computers, that are very big right now, so it's hard to tell. But there's still a lot of work to be done in application development. And if you take a long time frame, that's what we want to know. We want to know, well, how big a computer do you need? How long it's going to take? What problems are actually going to be relevant to to society? And a number of the programs across the agencies are really trying to answer this question. Next slide. So if you again, from a ideal policymaker world, you would know, at the size of the machine, the quality of the computer, what applications will start to matter for society. Right now we have a lot of proof of concept experiments going on. Soon, even today, we can do hopefully new science that we couldn't have done otherwise without quantum computers. And then the question is, well, what's next? When is optimization really going to happen? And what's our probability that it will really work out? There's still a lot of good research, open fundamental problems that need to be solved here for us to fill out this chart. This is very much an artist's rendition. Next slide. And that just brings me to the strategy for quantum computing. So I mentioned we had a strategy for networking, we had a strategy for sensing. Quantum computing, in some respects, is the most mature of the three because there's already been significant investment from government, from industry, and agencies have been thinking about these problems for a long time. But it came, so the strategy really had to be about what does the country need to do? How do we manage the potential of this new technology versus the risk of future quantum computers? And the net result was what we call National Security Memorandum 10. This is a presidential directive, or much like an executive order. Basically, the president puts out direction to the agencies that they need to follow during his administration. And the most important aspect of this is it sets a timeline for the agencies for moving the nation, especially their networks, to post-quantum cryptography or quantum-resistant cryptography. And the reason we needed to do this now is, even though quantum computers, that's a capability might be far away, is that it just takes a long time to convert to new cryptographic systems. It can take 10 years to decades to do it, and this is not going to be an easy transition. So that's one of the aspects. The other two aspects are sort of this reaffirmation that quantum is important, that we have to continue to move forward on the R&D, irrespective of the security. It's just so important. We don't know what the implications are going to be, and we have to do it, but we have to do it smartly. We have to protect the investments, and we have to, reconsider all the tools that the U.S. has for protecting investments, in this new era of fast-moving technology. And so, what makes sense to export control? What doesn't? Questions like that. Next slide. Just to reiterate, why do we have to do it? We don't know. It's not definitive that a false quantum computer is possible, right? But over the last 30 years, we have not reached a no-go or any physical limit that says that it is impossible, right? So you have to take them seriously, number one. Two, because of this timeline, this lag to move to new cryptographic systems, you can't wait. And in the United States, we tend to, especially for like the president's communications, we have to protect information for 25 years or more. So now we're getting to the time frame where these things matter. And then given that, the agencies needed direction on who should do what and who had the responsibility for moving different pieces of the cryptographic systems, the secure communications networks forward. All right, next slide. And I'll just end by talking about the international components. As I mentioned at the beginning, quantum has always been global, and we've made a big effort to engage with other countries who are putting investments in quantum or interested in getting into quantum more. And with around these main topics, workforce development. How do we lift all boats? We need more talented people in this space. How do we move the science forward by it's an extremely broad field. Even within computing or sensing, there are many different types of qubits, right, that need to be explored, and algorithms and so on. And then, how do we synergize our research security paradigm so we don't slow the field down, but we can all be safer. So we had an event in the White House this past May where we brought as many countries as we could fit in one room, given COVID protocols, to just talk about, have a first conversation about these topics. And there's been a series of these international meetings, just talking about the problems facing the field and the opportunities, and how do we communicate this to the political leaders who are making these decisions in this country. Next slide. So that's the end, but I just want to end by saying, to me, quantum is more than quantum. People say, well, why are you putting so much effort into this nascent field that we don't know its impact? And I think one answer to that is, well, the first thing I said, which is foundational shifts in information technology don't happen that often. And when they do, you better take it seriously, because we know what happened last time, right? The second thing is, the second argument is, you're not going to lose by investing in the skill sets needed to build quantum systems, right? If you think about what it takes to build a quantum sensor network or a quantum networking system or a quantum computer, those skills are physics, computer science, RF, radio frequency engineering, microwave engineering, microelectronics design, material science. Those skill sets are readily applicable to many industries of the future. Future microelectronics, autonomy, AI, robotics. Like, if you get skills in any of those areas, you're a deep technical expert in any of those areas, you will have a good career. I guarantee it. So it's a very good investment no matter what. And quantum is a very, sort of like the emerging, like the tip of the spear that brings all these things together in very difficult, challenging problems. So I really think it's a great example of the future emerging technology, where investments in quantum will just go beyond just the field of quantum information science. So with that, I'll end and say, we put, on the next slide, we put everything we are doing up on quantum.gov. In the US, there's a lot of legislation that's happened in the last year or so. We passed the Chips and Science Act, which puts a lot of investment in new infrastructure for creating chips, like microelectronics devices. And hopefully a big part of that will be R&D for emerging technologies like quantum or AI or neuromorphic and so on. There's great potential for additional funding for National Science Foundation for technology development and DOE and so on. There's a lot of stuff going on, and we're actively thinking about, what would the second 5 years of the National Quantum Initiative look like. And then ending on the next slide, we put everything on quantum.gov. So please check out our page. We have a lot of great resources there for World Quantum Day, if you want to participate next year or interested in workforce development programs. And we're really working now on developing clearinghouses for opportunities for fellowships and so on between countries. So please get in touch if you're interested in that. And happy to take any questions. And thanks again to the organizers.
Many thanks, Charles, for the great talk and the very nice overview. And then one of the issues being stressed at this conference, there are about 12 speakers coming from industry, is that there are many, many jobs in private industry, in companies, and therefore many students, even with a bachelor's or a master's, they can get reasonably good jobs in growing areas in many companies. So now, regarding the issue of international collaborations, so you mentioned seem to be mostly so far Europe and Japan, not correct? There might be some other initiatives in the future, perhaps including Africa or South America or some other areas, but
we're okay. There's kind of two timelines that are going on in parallel. One is talking to people, so we're talking to many different countries. The other is this multilateral meeting where we had, which there the kind of the cutoff, although it's impossible to do a perfect cutoff, was which countries had written down a national strategy for quantum.
Mm-hmm.
So each country or region has sort of a different stage of development. But we tried to, the kind of the first meeting was really about, well, what is your strategy and why did you do it this way? And let's share those. So I think as more countries to develop an internal approach for how they're approaching this field, that list will grow. And the list is of people we're talking to. Also, just doing agreements and stuff takes a long time, and there's a lot of political things. We're also talking to many other countries as well who are interested in quantum or making investments or interested in getting in and figuring out where it makes sense to coordinate. So some of those things are done through bilateral agreements like the quantum cooperation statements, but there are other things are done through other mechanisms that the US uses, like the Quad, which is India, Japan, Australia, in the US. There's some quantum mentions in there and so on. So there's all these types of international agreements, science agreements that are already in force that we can use without having to do bilaterals.
Yeah, great. So I see one question in the chat by Abdullah Tounsi. His question, how do you value in US NQI the different quantum technologies? I think meaning how do you compare them? Or which one is the most promising for future applications? I mean, this is a tricky question.
Yeah, it's a tricky question. And the answer is the White House doesn't do that. And this is what I was trying to say at the beginning when we have this federal approach where each agency have their own mission. So at the end of the day, the technology that matters to you, the best for technology, quote unquote, is the technology that's best for the mission. So if your goal is precision navigation and time, like you want to make a better global positioning system, then you should invest in atomic clocks, probably AMO type systems, next generation quantum sensors based on quantum mechanics. So it's a very different answer than if you want to make a quantum computer to do chemistry, right? So it really depends on the problem that you're trying to solve. So each agency runs programs sort of geared around the problems they're trying to solve. So there's no correct answer in a sense, but the way it happens in practice is that the agencies have problems to solve, they put out calls, and the best technology wins over time because it develops them, eventually develops into the most capable system.
Any more questions from Kigali? I do not see other ones.
I have a question.
Go ahead.
It's kind of, okay. So do you think we'll be able to progress very far if you exclude a significant chunk of the scientific community? So for instance,
yeah.
You know what I mean, right?
I don't think, I know what I can guess what you mean. And I want to stress that we're not trying to exclude anybody. I think, the whole point of these research security discussions is how do we maintain an open research science environment across the whole world? How do we continue to collaborate on the science problems that matter across the world with any country? And the concern we have to address as scientists, which is a real concern, is that there are some countries who want to take advantage of that openness and don't reciprocate. So the scientific model, as I was trained, is you go be an apprentice for a postdoc or for a professor somewhere, and then you go form your own lab. And there's a historical connection. Like, you're not going to steal his or her stuff because you want to maintain good relationship. Eventually you want recommendation letters and so on. There's sort of international norms that what it means to be in the scientific community. But if you're not willing to play by those, how do you maintain this open research environment that we all agree is better for everybody in a world want to play by those rules? And that's really what it's about. And there's no perfect answer. And there's a serious concerns like you've expressed are valid. you know, that why add all these restrictions? And I hope they're, you know, I'm not necessarily in charge of setting these restrictions. You know, our job is really to say, like, what will the impact be of these things you're proposing? You know, our export controls really make sense for this field that's just emerging. You know, what is the impact? That's really our job. And I think your point you're making is very valid, that, you know, we have to be very careful that we don't destroy this amazing thing we've built, which is an open science research community that moves fast. And at the end of the day, it's about people, any number of people. You know, again, I'm an immigrant, the result of an immigrant, and that's, you know, generally a good thing, and we want to continue that. So I hope that's an answer to your question. It's really not to be, the goal is not to be exclusive. The goal is to address these concerns that are being raised in a way that is the most, you know, the best for science at the end of the day.
Yes, this is fine. Thank you very much. I think there are two more questions in the chat.
Yeah,
Franco?
but one of the questions, I think Charlie already addressed it. There is Itamar Halevi was writing about the issue of collaborative efforts versus competition, which I think Charles TAHAM already issued that. I mean, they are supportive of collaboration, and they're also being aware of competition. And then the last question is, nowadays, by Dev Dut, nowadays, edge computing is supposed to be more secure than the global quantum internet. I'm not sure. Quantum edge computing might also be possible. What is the USA futures policy on edge quantum computing or edge classical computing? I'm not sure about if I understand the question, but
yeah, edge computing is supposed to secure. I don't know anything about edge computing, but I'll just say something about global quantum internet versus quantum resistant cryptography. So in that quantum networking strategy or approach that we put out, it sort of sets the policy recommendations from the quantum subcommittee here. And it says, look, we consider quantum networking, like quantum key distribution, entanglement based security, to be a very interesting and promising research area, but not ready for deployments for international secure communications. And many agencies now have come out saying that. And so the US strategy outlined in that directive I was telling you about, that steering memorandum on quantum computing, is really to move towards classical quantum resistant cryptography, while we explore at a research level quantum networking for communications. So right now, you know, security is really being built about deploying of classical codes, not quantum networks. And that's the key thing here. You know, you don't need quantum to secure against quantum. You need just new types of cryptographic systems, not based on RSA or public key cryptography. And that's what the US is pursuing. And NIST is running a global standards process to decide on those. And they've just decided on the first 3 suites of algorithms, which are very international teams who develop those, you know, completely open source, so that the whole world can benefit and move forward.
well, the questions have been all addressed. We're very pleased and honored to have Charles TAHAM with us, giving us a very nice overview on issues like research, policy, education, international collaboration, etc. So it has been a great pleasure to have you here, and thanks.
Thank you very much. Appreciate it.
Okay, good.